Okie dokie. Well, here we go. Let's see what we got here. Um, I've got it all built, and I've already gone through all the preliminaries and everything like that. So I just built it, and I didn't worry about the high speed, fast action, whatever. Let you guys at this point, card 6, you should have it sorted out, sort of. Any rate, here's the rheostat. I did it first because it's got 2, and then here's a potentiometer. I did it second because it's got 3. Here's a motor. This one's out of my normal teaching materials. Just a 12-volt motor. You can get it any different. Pull them out of a toy car or something if you want to. Built my little fuses here, and trust me, I've needed them in the past because I have made mistakes. I got a master switch here. I got the battery hooked up straight so I can, avoid creating huge problems for myself. I'll do the I'll do the rheostat first, and I'll do the rheostat first. Sorry, blah blah blah. Oh, whatever. And then we'll come down and we'll do the potentiometer. Got the voltmeter set up here. Hopefully we'll be able to read it. The key here is to show you that whatever the speed is on the motor, the rheostat voltage drop and the motor voltage drop have to add up to my source voltage, which for the sake of argument at this point is off of a battery is 12.49, 12.5. Okay, so it's going to drop a little bit when the motor's running and so forth and so on. But at any rate, the first thing is notice that the slot is at the sort of 7 o'clock position here. And if I turn it all the way this way, then it's sort of at the 5 o'clock position. So this would be dead center. Okay, pretty much anyway. This, on the other hand, does not have a slot or anything. It's adjustable so that you can set the trimmer and then set the knob exactly where you want the knob so you can move it. So this doesn't particularly have a center point. This one, on the other hand, can catch on fire because it only can handle so many watts, and depending upon what's running here, this motor may be drawing so many amps that this this rheostat can't really handle the heat because it's not a very high. Let me see if I have it here. 25 ohms, 3 watts. Okay, so that's not a lot. If I wanted to do the math on it, let me see here. I've got watts equals amps times volts. 3 watts equals some number of amps times, let's say it's going to drop 6 volts. So we move this over here, so we get 3 over 6, which is a half, so it can handle about 0.5 amps, assuming I did my math right. Okay, so if I go above a half an amp, this thing's probably going to get very smoky. And I've done it. Trust me, I've done it more times than you can count. Here we go. Now the motor's running, and you can tell, okay, that it's at half. Now I don't know, this is 25 ohms. I'm not sure what the resistance is here. I could measure the amperage, and I could tell you what the amperage is, and we could do all the math, and we can probably do that. But the first thing to understand is, as I turn the resistance down, the motor speeds up. And as I turn the resistance up, the motor slows down. So that's the variable resistor. I'm varying the resistance. Okay, now I can't measure the resistance when it's running. Okay, there's full speed, and there's like slow speed. So let's just, for the heck of it, let's go. There's that. I don't know. I'll put it back in the center. We'll see what we got. Okay. So let's see what we got. The full source voltage is 12.27. The voltage drop across the potentiometer is 4.0. So 12.27, remember this is easy math, 12.27 minus 4 should be about 8.27 or 8.3 across the motor, and the answer is 8.3 across the motor. Okay, now to prove to you that the amperage changes, well, no, I'm going to do that in a minute. watch what happens as I slow the motor down. Nope, go the other way. Slow the motor down. Notice that the voltage drop across the rheostat is getting higher because it's using more of the energy. So if I go to 6.13-ish, that's about half. Then I should read about 6.27 or 6.25 here. A little higher, 6.3. So let me take this down. There you go, 6.17, 6.15. So that's pretty close, right? And it's varying a little bit. And there's going to be a little bit of fluctuation there. Okay, but notice that the motor's running slowly because it has inadequate voltage. I'm reading across the motor, voltage drop across the motor. Of course, I got to actually be there to do that and not let it slide off. When I want to go faster, here's full speed. Here's slowest speed. Okay, so it's running on about 5.6 volts. And we can do the math all day long if you want to. I mean, we can pick any number. Okay, it was 12.27, so let's raise this up to 8. Which means this should be about 4.27. Ta-da! Battery's dropping off a little bit, so we're going to be a little bit low. Because right now it's going to be about 12.26. Okay. So, yes, there's a voltage drop situation here. But yes, we're changing the resistance, okay? So now let's do it with amperage. And we see what happens here and see if we can do a little calculating, okay? All right, so it's running at a fairly constant quarter of an amp. All right, meter reading 260 thousandths of an amp. Milli is thousandths, remember that? So that's 260 thousandths or 0.260 amps. All right, milliamps are smaller than amps. So now if I increase it, speed, notice that like we predicted, more speed is more amps. And we're running at about 0.280 or, yeah, about 280 milliamps. The slowest speed we got is about 250 milliamps. So there's only a difference of about 30 milliamps there. That's interesting. I didn't really know that. So we're watching the amperage change. And the changing amperage is changing because we're changing the total resistance. And the problem we have is that you can't calculate the resistance of a motor by measuring it. You have to actually measure the amperage and then work backwards. So if I wanted to figure out the total resistance here, I would have to do it backwards. And I'd have to say that the total resistance here is going to be 12.25 volts. Volts over ohms equals amps. Volts over amps equals ohms. So 0.290 amps. So we do a little calculating here. Let's do a little calculating here. 12.25. Oops. 12.25 divided by my amperage, which is 0.290. Oops, 0. Now that's about a third. So I'm going to predict about 36, 37 ohms. Oh, I was low, 42 ohms because of that quarter. That quarter did me in right there. I didn't allow for. So it's 42 ohms. Okay, so the resistance in this circuit is 42 ohms. 42 ohms and 12.25 works out to be that. So we'll do 12.25 divided by, let's just say 42 ohms, and we get oops, I'll do it right here, 0.291, 0.285. See, so it's close, very, very close. Okay, so the math works, all right? You need to understand the math works. So what did we do? Well, what we did was we measured the voltage drop here and the voltage drop here, and we added them up, and they equal full source voltage. We did it again, we did it again, we did it again. So that's the experiment. Play around. And once you figure out how simple this is, you're going to get bored. And when you get bored, congratulations, you're learning. And once you get bored, that's when you start adding more motors and more lights and all this kind of stuff, and you create your own circuits and just go nuts and enjoy, you know, having a good time. But that is a rheostat because we're literally changing the resistance, which is, again, which is this. Okay? And we're seeing the effects. So we're changing the resistance to change the current, changing the current to change the speed. But even though that's what it is, we're still dealing with voltage drops. And that's what makes voltage drops so easy. Because what is this? This is a corroded wire. See here? If this was at full speed, okay, and then as the wire gets more and more and more and more and more and more corroded, all right, more and more and more and more corroded, then the motor slows down. And people want to think it's a defective motor. Now watch. Let me show you how the Load Pro works, which is why I pushed this method, because it's thinking it works. All right, so I'm going to unplug the motor by actually cutting it out, which is a little excessive, I guess. But now watch. You know the motor was running slowly. You know that the motor wasn't running at full speed. So watch what happens. Here's the problem. If I put the meter back on volts, which I should do in order for this test to work, and I go to volts, notice what happens. Even though this is here, and you know it's here, wait, oh, I'm such a dumbass, I am such a dumbass. I gotta fix this. See, there's the open circuit. But wait, this is why it's so friggin' cool. Look, as soon as I saw the open circuit, I went, wait a minute, that's an open circuit. I didn't go, gee, I wonder what's wrong because I'm so confused now. No, I went, that's an open circuit. Well, why is it an open circuit? See the ghost voltage? Ghost voltage isn't open. Drop the black lead to a good ground. It's still open. So the problem's there. There's my problem because I didn't turn the circuit on because I cut that and I didn't see that. That's why this is so totally, for those of you up in the New England area, this is wicked hot, okay? This is wicked hot because what it does is it lets you fix things without having to do a lot of guesswork, okay? So let me try to, hold on. Okay, so I turn the circuit on. Let's see if my open is gone. How do I know if I have an open? I have ghost, but notice, boom, full source voltage. Now let me back up. I'm looking for voltage. My voltmeter only method is look for voltage. There's voltage. Well, what does voltage tell me? What does this tell me? This tells me I do not have an open or short. Why? Because if I had an open or short to ground, this wouldn't be there. So the only thing that voltage tells me is no open and short. Now watch. Here's the corrosion. How do I know it's there? I load the circuit and, okay, there is the voltage drop. So that voltage drop tells me that I have a corroded circuit somewhere. Drop it to a good ground, repeat the test. Problem comes back this way. And I go backwards and go, there's such a, I lost it there, and then I kind of lost it there, and I kind of lost it there. But over here, guess what? I don't lose it. So where's the problem? It's between there and there. That's how stinking simple this is.